We are on to Unit 7, ladies and gentlemen, so let's jump right into it. First of all, the first 3 slides here are just kind of a review of geological time. So we touched on it just a little bit in the past, so let's talk about it a little bit more. So if you look at geological time, we start back when we believe the Earth was made, which is 4.6 billion years ago. And so from that point in time till now, what we've done is we've taken that length of time and we've broken it into chunks. And these chunks are what we call the geological time scale. And those chunks are broken up, and they're not broken up evenly. There's not a certain number of years in between each chunk. The durations vary, and they vary depending upon basically main events that occurred during that time. But they go from 4.6 billion years ago up to the present day. And so this is actually a breakdown of it on this page. This shows all of those different time periods, and you can see Jurassics are when birds first show up, the first mammals are in the Triassic. So you can see it's broken down according to those things. It's important for you to realize in all of this time scale, only this little piece up here at the top is where humans have existed. And so we're a very small piece of that. If you remember, we took a walk and put the signs in the ground all the way out to the football field, kind of illustrating some of the main events that occurred in this process. All right, excuse me, I have a cold. Let's get into section 1. So, section 1 basically is a nice little review of the Earth's structure and the dynamic nature of the Earth's surface. So, hopefully a lot of this is a review from you and you learned about it in your past science classes, but if not, we're going to talk about it a little bit here. So first of all, the Earth itself. The Earth itself is broken into a series of layers. So, on the very inside of the Earth, down in here, there's 2 sections of a core. The middle or inner core inside of here is, the inner core is a solid. It's important to know it's a solid. It's made of nickel and iron, mostly. From that, you go to the outer core, this next layer out. It's a liquid now. It's also iron and nickel, but it's a liquid. They're both extremely hot. The inner core is actually hotter than the outer core. The outer core is a liquid, the inner core is a solid. That messes with some people's mind, but it's a lot of pressure. The pressure squeezing in turns the inner core to a solid. From that, you go out into the next layer out, which is like this section right in here. It's referred to as the mantle. If you want to think of this thing like an apple, okay, the core of the apple, where the seeds are at, are the inner and outer core, and then the meaty part that you actually eat, the mantle, is this layer right here. And the mantle is where a lot of action's taking place. Some people call it a liquid rock. It's a pliable rock. It's kind of a plasticky, amorphous solid. It's kind of in that tweener phase. And what it does is it actually moves around in there. And that's what transfers heat around inside the Earth and then to the Earth's surface. And then the outside of the surface, the actual stuff we stand on, is the crust, which is a solid. And so it is made up of different kinds of crust. There are 2 flavors of it, continental and oceanic. Oceanic, usually very thin crust, and it's also very new crust because it's constantly being melted and remade. By contrast, continental crust is thicker, quite a bit thicker, and it's lighter, which means it always floats as high up as it can. This continental crust is heavier, and so if they ever bump into each other, the oceanic crust will get pushed underneath, continental crust will stay on top, and as a result, it always floats on top, and it is very old. The oldest rocks in the world are on continents. Actually, Australia has the oldest rocks on the planet. And so when we talk about those plates and they're moving around, that continental and oceanic crust moving around, we use a theory called the theory of plate tectonics. That there's these big, huge chunks of Earth that are sliding around and moving. There were ones stuck together in this big supercontinent called Pangaea. And from that point in time, they've been moving around, and they've been moving around because of convection currents inside the mantle. The mantle has rising and falling magma, and it creates this circular pattern, and the crust is riding on top. So as it goes in circles, it pulls the crust along with it, moving it back and forth and around. And there's lots of evidence to support this. First of all, the continent's edges fit together like puzzle pieces. South America and Africa, for instance, they line up really well. They have fossils that start in parts of South America and they extend into Africa in bands or strips. I actually have one that starts here and goes all the way through Africa and then goes into Antarctica and a bunch of other places. And so matching fossils. In addition, matching rock patterns. They actually look at the layers of the rocks in these different areas and the mountain ranges. And they see that they line up from one continent to the next. And then there's evidence of climate change. There's glaciers in the middle of Africa. There's fossils of ferns in the middle of Antarctica. Things that show that the climates are different and suggest that the continents could be in different places. And so these are the actual plates that currently exist. There's about 12 major ones. We sit on the North American plate. And so they're constantly moving towards and away from each other, smashing together, and along all these plate boundaries are where you get all the action. This is where most, not all, the vast majority of earthquakes and volcanoes occur along these cracks or layers or boundaries. Here's an example of one of those interactions. This is where a plate is coming together with another plate. So you can see here's the oceanic plate. You can see this dark layer. That's how thin it is versus continental crust. You see that it is much, much thicker. Okay. So when they bump into each other, when they come together, so this one's going this way and this one's going this way. When they come together, the heavier one will get shoved underneath. When it gets shoved underneath, it actually melts and then works its way back to the surface. And you actually get volcanoes as a result of it along this area. In addition, it kind of squeezes the continental stuff in, forming mountain ranges in addition. And so you get that action happening. And here's actually a picture. This plate's going this way, and you see there's a crack in there, and this other plate's going this way, and this is actually a diverging plate. This is what we call a mid-ocean ridge, where it's separating or having seafloor spreading happening there. And so we have actually some volcanic activity that comes up through this section as well. So here's a converging plate, and there's a diverging plate. And the important thing to realize is when these things happen, you get all of these cool features on the Earth's surface, like mountains and volcanoes and mid-ocean ridges. And right here, this little scar where this one's going under this one, called an oceanic trench. So all of these different physical features occur as a result of these plates moving around. So I just talked about this a little bit, but diverging plates, or where plates are moving apart. And so this crack right here is your mid-ocean ridge or your Rift Valley. So there's the mid-ocean ridge in the center of its Rift Valley. And you can see on this picture down here, all of these dark blue lines are examples of diverging plate boundaries or mid-ocean ridges under the ocean, where the things are spreading apart. By contrast, we have converging plate boundaries, where things are coming together. And this really forms one of two things, either folded mountain ranges or volcanic mountains. So volcanic mountains, if it happens between two ocean crests and one gets pushed under the other, it pushes up these and creates melting and actually creates what we call a volcanic island arc, where this is actually occurring. And I showed you the picture earlier of how it happens along the continent and still forms volcanoes. So the two incidents are quite similar, melting and volcanoes and mountains being built in both instances. And then the last one is transform plate boundaries. Transform is when they slide next to each other. So this is the San Andreas Fault in California. And this part of it is going this way, and this part of it's going this way relative. So they're scraping next to each other. And when that happens, you don't really get any volcanic activity like you do with the other two. Instead, you get lots and lots of earthquakes. Okay. And so this action that's happening inside the Earth, all this moving around of the mantle that creates all of these cool geological features, the internal geological processes, the heat rising, the heat generated from the interior of the Earth that's working its way up, is what's creating all these Earth surfaces, all these reliefs and changes in elevation, and all that kind of stuff happens because of the stuff happening inside the Earth. External geological processes, these are the things that are happening on the outside, actually do the opposite. So this one actually builds things up on the surface, and then the stuff that's happening on the surface, wind, water, rain, erosion kind of stuff, is what is actually wearing down the surface of the Earth. So if this process ever stops, what it's going to do is eventually allow the surface becomes smoother and smoother and smoother. And so that happens through a process called weathering, where the rocks get broken down, and they can get broken down a variety of different ways. But it's typically caused by two things: the sun and gravity. And those two things come together to create weathering. There's actually three flavors of weathering. There's biologic weathering, chemical weathering, and physical weathering. And all three of them have an impact on the breaking down of materials. And then they move around after that. So, I already mentioned volcanoes a little bit, but volcanoes specifically are just vents. They're just vents in the Earth's surface that is allowing heat in the form of melted rock, typically lava, to come out to the surface and cool down. And you'll see right down here, there's all these red dots on here are examples of volcanoes, and you can see that the vast majority of them sit along, actually these are the plate boundaries, the cracks we were talking about in the Earth's surface. And so they align quite nicely with that for us. There are a couple of exceptions to that. Hot spots are one, but we'll get into that later. In addition, we have earthquakes. Earthquakes occur where a fault or crack is at, and then the pressure builds up there, and then it breaks. And when it breaks, it releases what they call seismic waves. That's the energy that comes out of it. And it comes out of it in the form of three seismic waves: P waves, S waves, and surface waves. P waves are known as primary waves. They're compressional waves, and so what they do is they're called primary because they're the fastest wave, so they're the primary or first to get to a seismograph station or wherever it's located. S are secondary waves. They move a little slower. And last are surface waves. And surface waves are the actual ones that cause the damage in most situations. So P waves are compressional waves, and they actually smash and compress and do this with the Earth itself as the wave moves down. S waves actually snake up and down and up and down, and they cause this kind of motion as they work their way through things. And then the surface waves actually create a rolling motion, and that's what causes the damage. That's it for now. Thanks. Stay tuned.